This is part 3 of my video series on this most recent summative about power, impulse, and momentum. And I'm going to be going over the third page in this video, and let's get right into it. This person in this image is wheeling the wheelbarrow north. It's full. And then he dumps the dirt out and then wheels it back south with the same speed. The magnitude of the momentum on the way south is less than it was on the way north. And there's a couple important things to notice about this simple relationship that is how we calculate momentum. When we say magnitude, specifically, we just mean the actual numerical value we get, not the direction, positive, negative, north, south, or anything, just the magnitude. So on the way north, m is quite large because the wheelbarrow is full. And then on the way south, m is much smaller, but we know that the speed is the same. That is, the magnitude of the velocity is the same. So less on the way south than north. If the net force is acting on an object in the opposite direction of motion, then the object's momentum will decrease. And this relationship here, this is the impulse-momentum theorem. And I've expanded the right-hand side to show the final momentum minus the initial momentum. And notice that if the direction of motion, that is these velocities, if the force is acting opposite those, then we expect that the left-hand side of this equation is going to be negative when we do this computation, if we assume that these velocities are positive. And so what that means is if the left side of this equation is negative, then the change in momentum is negative. And so that means that the initial velocity is bigger than the final velocity, because then when we subtract these, we also get a negative. And just note, thinking about if you apply a force on an object and it's in the opposite direction of motion, the object's going to slow down. It's going to be going a certain speed initially, and then it's going to slow down. So that also means that the momentum decreases because the speed decreases. These first two free response questions are meant to just sort of get us warmed up. Each of them is really just involves a single basic relationship, that is a single formula, and there's a couple of little twists. First of all, on the first problem, we have to mind our units. We've got kilowatts here, and if I'm going to do my calculation using SI units, which I always recommend, then you're going to have to convert that to watts. Also knowing that if you do your calculation with SI units, you should surely end up with a time in seconds. But we are asked specifically for how many minutes. So there's a little twist here that you got to read closely and make sure you're answering the question that you're asked. But either way, we start with this formula for power. We want to know how many minutes it takes for something, a motor with this much power, 12.3 kilowatts, to do a certain amount of work. And so I solve this equation for time. That is, I multiply both sides by t, and then I divide both sides by p, and I'm left with the relationship here, just using a little algebra to manipulate it. Then I can plug my numbers in, and again, I plug them in using the SI units, and I get a value out, SI units, rounded to 3 significant digits. And then I can convert this from seconds to minutes just by dividing by 60, and that's where this number comes from. In this second problem here, again, it's just a matter of using this very simple relationship between, it's really the definition of momentum. And we're actually given our quantities in using the SI units already. What makes this maybe a little bit more challenging, there are two things. One, we have to consider that there are only going to be 2 significant digits in our answer, because one of our these values that were given has 2 significant digits and the other one 3. But we're only allowed when we divide to keep the least number of significant figures that we start with. So that is 2. Also, whenever you're calculating a velocity, you should include a direction, a magnitude and a direction. So I was a little bit generous in this problem because I didn't take points off for people who got to all the way here to 46 meters per second but left off the direction. But just a reminder, definitely include the direction when you're talking about momentum or velocity, particularly in the context of the problem. Here we're told that the momentum is in a particular direction towards home plate. And so the velocity is also going to be towards home plate. It's in the same direction as the momentum in this problem.